Hello everybody, my name is Kyle Shorey, and this is my lab number 4 on bar magnets. Alright, so first I'll introduce the lab, go through the procedure, the computational model I used, the errors, and then what if and what it mean questions. Alright, so to start off, the lab mainly focuses on the electric field of a bar magnet and the distance dependence of magnetic fields. To do this, we used observed and predicted distances, as well as the Biot-Savart law, which basically states that a tiny current is proportional to the length of the current element. So preview of our results, mu, we got 152 amperes times meters squared, and n, we got 0.065, which obviously some discrepancies there, and I'll go into later why we had those. Okay, so here you can see the diagram for a magnetic field on a bar magnet, and this is essentially what we're looking to get out of our computational model. In terms of the procedure, we started off by just getting the necessary materials. Then we had to compensate for the Earth's north pole, magnetic pole. So we used a compass and then lined up the meter stick so that it was perpendicular to the north and south poles, added the magnet on one end of it, and then we used a magnetometer on the phone to essentially measure our distances for where we found the readings for B that were given to us by the lab instructions, and then put it into a spreadsheet, calculated the magnetic moment, and then we used a starter code. And then some of the assumptions we made while running our experiment were that a bar magnet can be treated as a magnetic dipole, and that the only magnetic fields are coming from the Earth and the bar magnet. So our system is the bar magnet, and our surroundings are everything else. All right, so here are the formulas that we use. As you can see, the dependence equation we got from the graph was 0.065 x minus 10.4. We know that in our ln, our linearized equation, n is the slope, which is 0.0565, and then ln of k equals a y-intercept, so we solved for k to get 3.04 times 10 to the negative fifth. And then we set the two equations equal to each other for distance dependence and then magnetic field, and solved for mu mag, which was 152 amperes meters squared. Here we have the computational model. So we started off by entering our mu mag that we calculated, had to make a function for the dipole B, essentially calculating what the magnetic field was at each point. Then we listed out our different observation locations. We got the dipoles for each of those locations, and then we made the arrows for all the spots. And then after we did all of that, we found another location for 45 degrees. At an angle to our dipole. All right, and then so here you can see we have the glow script results. 4 cyan arrows are the perpendicular, the 2 orange arrows are parallel, and then the magenta arrow in the corner there is the 45-degree angle. All right, here are our observation statements. As you can see from here, 1 and 4 are the only true ones, basically saying the farther away you get, the closer to 0 it'll be, and the closer you get, the higher the number will be. So some potential errors and improvements are other electronics likely had magnetic fields that interfered with our measurements. Next time, it could be better performed in an open space with little electronics around, and the axes could have been measured incorrectly, which is actually what we did, which was what led to our discrepancy in results. Because we ended up aligning it with an indeterminate angle and not so that we ended up not actually compensating for the north pole of the Earth. All right, and then our what if questions. So what if we hadn't oriented the experiment to compensate for the magnetic north and instead had laid out our meter stick at an intermediate angle? This is actually what we did, but suppose that we had done the lab correctly, we would actually get completely different results. By compensating for it, we're able to isolate the x and y components for the bar magnet field pretty easily because we're canceling out the Earth's magnetic field. However, without this, we'd need an intermediate angle and use that in the calculations to actually figure out the net effect on the bar magnet. And then if we were to stick 2 identical magnets together end to end, we would essentially get double the magnitude, but no change in direction in terms of the magnetic field. Thank you.